Good afternoon, everybody. I'm happy to introduce the speakers for today. My name is Hani Nassif. I'm a professor at Rutgers University in the Department of Civil and Environmental Engineering. And I'm also the director of the Rutgers Infrastructure Monitoring and Evaluation Group, and also the associate director for outreach and research at CETO Smart Center at NYU. It's my pleasure to introduce today's topic on the fusion of structural health monitoring and WIM motion data for minimizing the cracking potential of concrete bridge decks. This is based on a couple of projects that we have done over the last maybe 20 years or so, or even more, about assessing what would be the best concrete pouring sequence for bridge decks so that the cracking potential will be reduced drastically, especially on bridges that are existing bridges where we are pouring concrete in adjacent lanes. Today, our speakers are going to be Dr. Chaikok Na, who's the Senior Research Associate, and also Mike Rosala, who's a full-time research engineer. Mike had a bachelor's and master's degree from Rutgers University, and and Chaikok now has a PhD from KAIST University and has been with Rutgers for more than 15 years, I would say. Anyway, the idea, I want to also recognize Reed Holland, who was my previous PhD student, who also was involved in this project and had a big role in the modeling and also in the field implementation. Without any further ado, I will let the speakers go ahead and start. Thank you.
Thank you, Professor Nassif. Hi, this is Chaikok Na. I'm going to cover the first part of the presentation, and then Mike Rosala will cover the other part. So, as you know, that Hani Nassif is the PI over RIME group, which is represent the Rutgers Infrastructure Monitoring and Evaluation group. And our team has been providing like forensic engineering support through compressive bridge evaluation using integrated multiple technology and areas of expertise. For bridge evaluation, we first need to know about how the material performs. Then we need to determine what's the bridge resistance using structural monitoring and also non-destructive testing. And also we need to quantify the loads applied to the bridge using the WIM motion system. And by integrating these technologies and the finite analysis can be used to develop strategy for minimizing bridge deck cracking. Next. So in this webinar, we'll discuss several areas, including the WIM motion, structural monitoring, material testing, FEM analysis, and multiple agendas, and all working toward one objective, which is the title, minimizing the cracking potential of the concrete bridge deck. Next. So first of all, I want to talk about the WIM motion system. This is measures the weight of the vehicle and axle loads, and while the vehicle is moving. And this is enabled to efficient traffic monitoring, enforcement, and infrastructure protection. And WIM can be used to understand the traffic loading pattern, including the movements and the extent of the heavy truck applied to the bridge. This information is very critical because although bridges are designed for legal load, many trucks operate at weight exceeding the legal limit, like 80,000 pounds in general, or sometimes shorter vehicle, the weight limit is like 50,000 or 60,000 pounds only. And this can accelerate the bridge deterioration and reduce service life. So and another thing that we will mention about the WIM is this can be used as the direct overweight enforcement. And the slide on the right side shows the first in the nation direct overweight enforcement site in New York City along the Brooklyn-Queens Expressway. And for this particular site, when the overweight truck passes, the system can identify the vehicle weight, license plate, and owner and other information. And the notice of liability will be sent to the owner and resulting in like $650 or $1,300 of fine, depending on the number of violations. I hope we can have another session about this overweight enforcement in the near future. Next one. So there are, for the WIM, there are different types of sensors. In general, in the past, the piezoelectric, the marked as a P, purple, is the mostly used in the field, and other coarse sensor is recently used last 10-20 years, and the low cell and bending plants have been using a lot in the past also. Their performance and the maintenance, everything is different. If you click again, yeah. So I just to distinguish them, I categorize them into four different things, and for the installation, lifespan, maintenance, and accuracy. Just rather than going over each item, just to make it sure that the piezoelectric is easy to install and then is to maintain, but the lifespan is short and accuracy is not as good as others, while the rest are is a bit difficult for installation, but the lifespan is much longer and accuracy is good. But the core sensor, the one on the left bottom, that one has less maintenance, similar to a PVDF sensor, while the row cell marked as L and then the bending plate marked as a B, red. It's kind of hard to maintain because PVDF sensor and core sensor, everything is enclosed within the structure, while the low cell and bending plates, they have a lot of many mechanical components embedded within the system. So they have to maintain not only the pavement but also the components of the WIM sensor. So that's why that's how we can distinguish between them. And that I think these days, and from our perspective, you are generally using the core sensor, while low cell and bending plates we are not using as much for our research. And so as I mentioned, we mainly utilize PVDF sensor and core sensor for our research, and that's depending on the project requirement and the budget. So, and this slide shows the installation of the example of the PVDF sensor, and from left top to the right is after drawing, cutting, drying, and then install the sensor and grouting, and that's almost finished, and it's very easy to install. Then the bottom part shows the final installation layout and the field view of the sensor. And then left bottom is the picture while we are testing is me and Mike Rosala in the picture. And the other one is the core sensor. The next slide, it's a bit more extensive work than the piezo sensor, because the piezo sensor is very small sensor. It's about 1 inch wide, 1 inch deep only. But this core sensor requires about 3 inch wide and 3 inch deep cut, a bit more extensive work. So, but the process is almost the same: drawing, cutting, drying, and installing and grouting. And at the end of the work, at the left bottom, that we need to grind the top surface to make the smooth surface, so that we don't have any bump on the sensor to get a better results. And the right bottom shows the final layout picture that is similar to the piezo sensor, but this has the core sensor embedded. So there are the sensors are different, but the way it installed is the same, and it needs a lot of coordination between the installer and then the contractor and who own the roadway or bridges, etc. But this is very this is very required for this type of work to minimize the cracking of the bridge deck. Next one, please. And every sensor requires a calibration process to know how to improve the accuracy of the sensor and the reading. And like SHM sensors, stochastic monitoring sensors are typically calibrated under laboratory conditions to determine the factors. However, the WIM are installed in the field and must be calibrated in the field condition. And the payment characteristics and site-specific constraints vary from location to location, but this is why we need to do the calibration. You can click the video. And this slide illustrates the calibration process. Use the truck on the right side, the same as on the left side. So truck passes over the sensor that we do multiple times, depending on the speed, position of the lane, everything. We determine the factor, and that is used for the future weight measurement from the weighing motion system. And after calibration, the system can provide vehicle classification, axle weight, gross vehicle weight, and the axle load, and then truck length. And then the right screen shows the live view of the traffic from the system that we are using for our testing. And this can also can be improved later, for uh, to track the different things, including deflected tires and position of the vehicle along the lane. But this is another topic that we may have chance to talk later time. So how can we use this WIM data in our case the objective is to minimize the cracking. So the concrete cracks when the applied stress exceeds the strength, and the stress is induced by the truck loading, while the strength is determined by the material properties. This WIM data provides information on frequency and extent of heavy traffic. And the two table here on the left and right shows the histogram. It's not typical histogram, but histogram of the heavy truck traffic. So if you see it on the left side is weekday traffic and the right side is weekend traffic. And the second column tells total truck is the number of truck per hour. Over I think at that time we collected about a couple of months of data, and we and the on the weekdays the traffic start increasing like 4 5 a.m. and then peak at around 1 to 3 p.m. and then it reduces about 7 8 p.m. It reduces. On the weekend side, the traffic is almost 1/5 of the traffic during the weekdays, and then we can see how the traffic changes during weekday and weekend based on the WIM data. And also, if you look at the red color in each weight limit, 80, 90, and 100, they are showing if it's full, it means more than 20 vehicles, and then if it's less, the size is proportional to the number of vehicles. I just see that during the daytime, 10, 11 until like 2, 3 p.m., there are many heavy traffic over 100,000 pounds, even 120,000 pounds. There are one or two trucks every hour like that. And other times, the weight is much less and also number is much less. And on weekends, similar pattern happens. Can you go back? During like daytime, 1 to 3 p.m., there are more heavy traffic, and the rest of the day there's less traffic. And so next one. And we look into more closer on weekend data, Saturday night and Friday night until Saturday and the Saturday night until Sunday night, because we this data is to provide to the contractor to determine when they pour in order to minimize the truck loading so that the deck does not crack, or to minimize the cracking. So between Friday and Saturday, we see the Saturday to Sunday traffic is much less, and we don't see many or almost no heavy traffic over 80 or 90,000 pounds. On Friday, there will be more trucks. There are more heavy trucks. We found more trucks on even at night compared to Saturday night. So based on this information, we recommended them to pour the deck that is critical on Saturday night until Sunday, while the less critical bridge member they can pour on Friday until Saturday. But we do not recommend to pour anything during weekday, because as you saw in the previous slide, the heavy truck is extremely higher than weekend compared to Friday and Saturday. So this is about the weighing motion data, how we can utilize this data to plan for their deck pouring to minimize the cracking on the bridge deck. Mike.
All right, so thank you, Chaykuk. I'll be taking it from here. So we're going to enter the SHM portion now. So what SHM is structural health monitoring, and it's typically used to assess the condition of the infrastructure. We collect data from sensors installed in or on the structure, and we can analyze that data to detect anomalies or damage. But in this case, it provided insights for complex analysis in order to reduce early age cracking. So we instrumentize this bridge. We collect the data and we use it to calibrate a model, specifically a digital twin of the structure. And this allowed us to do cost-effective analysis of this complex structure and run a lot of different cases in order to find the conditions that minimize any potential cracking. So we use a wide variety of sensors and techniques for this. We primarily use strain gauges. You can see at the top, we have gauges that can be placed inside the bridge deck that attach to the rebar. We have gauges that can it could be bolted onto the girder elements or even clipped onto flanges. We use that extensively, as well as accelerometers were used often in this project. They can be placed inside the bridge deck, but also clipped onto the girder elements. One of the novel things that we did with this project is we use a laser Doppler vibrometer, which we'll get into in a later slide. And in past projects, we use linear variable differential transformers, so LVDTs, to measure deflection. So deflection is a very good way to verify that the strain values that we're getting are correct. So it's good to get multiple sources from different types of sensors to cross-reference. And while we didn't use it in this project, we have used many times multiple probe corrosion sensors and tilt meters and geophones. So I'm not going to get into too much of the detail, but just to give you a brief overview of what the strain shim testing looks like, we can see at the bottom the sensors that are applied to the flanges of the girders, floor beams, stringers, wherever we need to calibrate our model. And you can see some of the results. We can see that as the truck passes over the span, the strains peak in different locations. And since we know what those locations are, we can use those to calibrate our model. This is for this advanced analysis, but typically this can be used to detect any anomalies or damage or any other problems that might need mitigation or remediation. So these are two examples, and you can see there's a dynamic influence with the up and down motions of the truck going across, and a lot of good details that you can glean from that. So going to the laser Doppler vibrometer displacement testing, it's a pretty easy to use system. It's a little expensive. Professor Nassif led the usage of this type of technology actually in some ways. So under the bridge, you can place it, uh, face it upwards so it's shooting one of the girders, and you can measure the actual deflection in real time. And that's done through integrating the acceleration to velocity to displacement. And you can see some of those results at the top. Like with the static test, we can see the zigzagging from the live traffic, and then slowly a vehicle of a known weight parked onto the span at midspan, and we got ignoring the noise from passing traffic, we did get the structural response and displacement, and you can see it leave the span slowly at the end there as well. And as well as dynamic testing, where we can observe the effect of live traffic and isolate a truck that we know its weight when it passes, so we can get the dynamic response. So all of that kind of comes together with the strain testing. And another thing is the accelerometer tests. These are very useful. They're very easy to use. They can be put onto the structure multiple different ways, and it's good for dynamic loading. It's very accurate. It could be integrated once for velocity or double integrated for displacement, and you can really see the dynamic effect of a truck moving at full speed crossing the span. So that's useful information for our purposes as well. So that's leaving the shim section behind. Now we're going to move a little bit more into the maturity testing and non-destructive testing that we did. So what maturity testing is a type of non-destructive test to estimate the early age and in-place compressive strength of a bridge deck or infrastructure component by monitoring its temperature history over time. This is a very useful technique. It has a very low cost of entry, just temperature data loggers and a previous short study just involving compression samples. So you can see a little bit of that summary below, but I'll go into it a little more detail on the next slide. So this is a summary of a study that we did actually for the mock-up test recently. So temperatures were collected for the slab and the cylinders, as well as the ambient conditions. you can see that after the concrete sets, the strength gain or the temperature gains rapidly due to the heat of hydration. And we take note of all these points. We collect all the data minute by minute, and we add up the cumulative temperature over time. Uh, then early age tests are done on compression samples of a known temperature as well. So 8 hours, 12 hours, 24 hours, and 3 days. So typically with DOT, it's 7 to 28 day testing. In this case, we're looking at much shorter. So very early from set time to 3 days. That's the optimal window to do this early age testing. So once we know the compression strengths and we know what the temperature over time they were exposed to, as well as the concrete slab that we're interested in testing, we can use a temperature time strength curve. So as the concrete gains strength, we know how many Celsius hours it was exposed to. We can create this curve for a known formulation, and every time you use that formulation in field, in fairly similar conditions, you can accurately predict what the strength is going to be in situ. And then in step 4, you can see an accurate estimate of what the slab strength is over time. So this can be very useful for verifying opening or moving to the next construction staging if that's required. So we're going to go over another study using a little bit more of this temperature data. We can see we had different cylinder temperatures. We could see that in July it was very hot, obviously, midsummer, very hot day. The cylinders got up to 140 degrees, so very hot. And then in May we had another test, an overnight pour, and you can see a long duration where the cylinders were fairly cold actually, and only peaked at like 15 hours or so at midday the next day. So when we compare this to the internal temperature of the deck, you can see that huge difference. The deck is a fairly massive piece of concrete. So when exposed to sun and the heat of hydration, you can see the temperature got quite high, just under 135 degrees Fahrenheit, while the cooler pores got much lower, only about 95. And this has a direct effect on the strength. We can see these 3 pores, span 1 and 2 or span 1 and 3 were in the cooler temperatures, and the July span was in hot temperatures. The hot temperature set in 3 hours and gained strength rapidly, while the cooler temperature is set in 5 hours and still a similar trend, of course, but just a little bit less. And we can see the importance of some heat, either from ambient conditions or the heat of hydration in the last point, which is the strength at 50 Fahrenheit. If concrete was kept at 50 Fahrenheit, it might set in 5 hours, but the strength gain is abysmal, which really showcases why thermal blankets need to be used and the temperature needs to be maintained under the blankets for that concrete to really gain strength in a reasonable time frame. So that concludes the maturity testing section. So now we're going to talk about long-term shrinkage and thermal flexing monitoring. In order to do that, we embedded strain sensors, which are another type of structural health monitoring equipment, and these can be used to identify long-term shrinkage or creep effects. We also investigated thermal flexing behavior, which we noticed can be consistent or can be significant for long spans, especially at early ages and in large temperature changing time windows. So for an upcoming example, we're going to discuss an early morning pour with a large daily temperature change, which is typical of summer, which is when a lot of work occurs. And it showed fairly significant strain at the midspan of the bridge deck. So going into how this was done, it's a fairly low cost study. It doesn't take all that much. It just takes some sensors embedded into the bridge deck. We put sensors above the girder to measure the effect the girder had immediately onto the concrete bridge deck above it, as well as in the middle of the concrete deck span and in the pour. So you can see the 2 different arrangements over the girder and in the slab array. The samples were placed in longitudinal and transverse, as well as maturity gauges were also done in this study. And you can see how they were installed in the bottom side view. They're placed underneath the rebar to protect them during casting. And you can see the plan view and the cross-sectional view on how they were located. So going into a little bit of the results for this, we wanted a control. We took a sample of concrete from that exact pour and we put it into a large 6 by 12 cylinder. So completely unrestrained, no rebar. The concrete was free to shrink as it pleased. So shrinkage was recorded at about 200 microstrain at day 28, which is fairly normal. It's sealed in it. It's just mainly the autogenous shrinkage, not drying shrinkage. And then we can compare that to the bridge deck, which was significantly less, 50 microstrain. And the question is, why is it much less in a bridge deck with restrained condition? There's a high concentration of rebar that, takes some of that stress. Um, but that's something that we need to consider because the concrete wants to shrink 200 microstrain, but 150 of that was taken by that rebar. And what happens is stress concentrates around that rebar and it causes a localized cracking, which is why we had that previous demonstration on HPIC. We want to lower the shrinkage as much as possible. So then less shrinkage is transferred to the rebar, causing localized development of stress and hairline cracks, which is um, would be good if it could be avoided as much as possible. So going into the bridge deck strain overview, we can see that over time, during ambient temperature, sunny days, things like that, the bridge deck does experience strain. It does thermally expand and contract. The structure below it moves, and we can see some of that here. We can see that a 40 microstrain is normal on a cool night into a hot day, and all the way up to 50 or even 60 for a very cool night and a very hot day over this for this specific bridge, which is a fairly long span. And we can see below that even though there is some noise, we can kind of get a moving average trend on the shrinkage over time of the concrete. So not just a thermal back and forth, but the general shrinkage over time. So that concludes the strain study. Going into the girder and flexure study, we put sensors right above the girder in the slab. We put them at the top of the bottom of the girder location, midspan of the girder on the web, and the bottom flange. And then we covered the sensors in thermal sheet so we can isolate the temperature. And that leads us into a little bit of why thermal flexing occurs. The top of the bridge deck heats up a lot during, solar radiance. There's a lot of energy that gets imparted of it during midday. It heats up, it heats the top of the girder up, while below in the shade, the temperature is a lot lower, and it's more influenced by the ambient air. So there's a large difference between the top of the girder and the bottom of the girder, and this causes thermal flexure because it lengthens on the top more than it does on the bottom, and the whole system can bow up a little bit. And this can be significant over long spans. For a real world example, if it's the worst case situation, like if you cast at midnight with a 5 hour set time, so casting here, it sets around here. So it's just first starting to get strength. It's just hardening. It's not fully, it's still green for better words, still fairly fresh. And then as the day heats up, it gains strength, but also the girder tilts up and causes tension at the peak midday. So for 12 hours after set time, there can be some microstrain that it's exposed to, and we can get into some of the results on what we believe caused some cracking. But there's nothing you can really do other than just watch the weather, but that's not always possible, of course. But for critical spans, it might be an additional thing to look into. So we can see the slab temperature mainly was controlled by solar radiation, of course. The sun puts in a lot of energy. The top flange was affected by the large thermal mass of hot concrete. and the web and bottom flange of the girder are more controlled by ambient, leading to this flexing. So we see the slab strains, top strains, and bottom strains in the top image. We can see that on sunny days, which are highlighted, or sunny days, cool nights, there's a large thermal fluctuation. And we can look down on the temperature, and we can see that while curing is occurring with the wet burlap, with the white sheets, that effect is mitigated significantly. The white sheets repel that energy. There's a lot less movement of the whole structure because the concrete's heating up less. So it's a it is beneficial and it's easier on the concrete if the structure is not flexing as much. If things are heating, expanding um, across its depth more consistently, it'll lead to less thermal flexure and more just axial movement. So once that sheeting and the curing is done, the top and the slab heat up more, causing a little bit more motion. So this is some interesting things that we found during this study as well. So going into the finite element model, what a finite element model is we decide to divide the structure into a finite element mesh. This can be solved for strain and displacement values. We use the SHM data at critical nodes to calibrate it. And once calibrated, it's almost like a digital twin of the structure. You can add different inputs and test kind of whatever you want fairly economically. You just need to be running a program and you can get interesting results and find what's beneficial, what's to be avoided. You can run a lot of different cases to find how to reduce cracking or really whatever it is that you're looking at. In terms of what causes strain and what causes problems. So we identified risk spots where we were worried that there might be some cracking. And this is based on just how the structure, the superstructure is established. So you can see some of that below on how that looks. And going into this exact project, we guided recommendations based on the construction staging in order to limit the potential for cracking. Because while one lane was being cast, others were had live traffic. So we were trying to limit that as much as possible, and we have some very good results on removing that. And it seems that the crack patterns were more so from thermal, but we'll go into that into this section. So what we learned from shim can be identified after it's cast, and we observe what actually happened. So crack mapping involves documenting the cracks and superimposing them onto a structure's plan, which includes their location, orientation, width, length, pattern, and evaluate their severity and mitigation techniques to repair them and make them inconsequential. Distinctive crack patterns can identify what caused them, whether it's drying shrinkage, early age cracking from different sources, overloading due to heavy adjacent live load traffic, thermal movement, and this can guide maintenance and try to avoid it in future, especially for tricky pours. So just to go over a little bit of the results, we felt that the crack pattern indicated more shrinkage and thermal action. It was more lined up in the midspan, and it was not lined up with the floor beam or superstructure elements, which would imply that it would be from the transfer of these forces from the adjacent live traffic. We provided recommendations to try to limit it as much, like Jay Cook said, onto the weekend, onto times when less traffic and especially overweight traffic is anticipated to just relax any of those stresses. But the stresses, of course, do occur from the different sources like shrinkage, thermal, and in this case, we felt it was more that as the primary driver. And there were hairline cracks throughout the structure, but they were very small, truly hairline. They were mitigated with MMA sealer, and even these cracks that are highlighted were very minor. They were just over in the second class above this one, so still not significant, and still the repair was just to use crack sealer. So we felt that in this project we successfully mitigated wide cracks from live loading and it was more just shrinkage and small thermal action strains that built up. So in conclusion, we felt that these advanced techniques can be used to better understand structural behavior, especially when you account for traffic patterns. And you can significantly reduce early age cracking from sources that you can control. And I'll go into some of these things right here. So optimizing the pour timing for sections with high cracking potential, like Chaycook mentioned, using the WIM data to identify periods with lower overweight truck traffic and more favorable thermal conditions if possible. That's probably less on the order of magnitude. It's probably more about limiting live loads, depending on how the superstructure is formed. And selecting concrete formulations is very useful to mitigate this early age cracking from shrinkage, which is basically the focus of HPIC, which we discussed in a previous webinar. So by reducing that shrinkage by half, that'll probably reduce it under the threshold for these cracks to form. Then the concrete gains its strength and can resist these forces without ever opening up with hairline cracks. So selecting mixed formulations are definitely a useful trait, and it's good to support it using maturity to make sure the strength is gained correctly. And if you instrumentize with a couple of these sensors, you can confirm that the shrinkage has been significantly reduced. By partitioning casting sections and alternating construction staging, you can minimize live load induced strain using these structural health monitoring and finite element modeling techniques. And crack mapping can identify potential causes of cracking and improve planning for future needs, which is really how you confirm what you did. In this case, we didn't have a control, so we will never know for certain, but just from what we were concerned with, we didn't see it. So we found it to be a big success in this project and projects in the past. And we're nearing the end, but and a little early, but we'd want to acknowledge New Jersey Turnpike Authority and Dewberry, which we worked closely with, and the whole gang, so the whole team from this time period, which was a big group. So it's a great time.
Okay, thank you, Mike, for this, Mike and Jacob. And we'll open the floor for questions. I don't know if you're monitoring the chat, Jacob or Lazy. Are we
Yeah.
getting any questions in the chat?
I don't see anything for now.
Yeah, so I have a comment based on this work. I believe in the past, we've had so many projects with the Turnpike and with the New Jersey DOT, which you acknowledged both of them through our, especially the New Jersey DOT for their bridge resource program, which RIME is the principal investigator on that. I believe that a rule of thumb that I kind of concluded over the years that there are three elements really that we'll need to worry about in terms of bridge deck cracking. One of them is, of course, the live load, and one of them is the shrinkage, depending on the material type, the mix that you are using. And the third one, which in my opinion has been from our measurements, has been the most, the largest, I would say, is the thermal. And so it depends, when do you pour your concrete in the winter or summer, and what would be the strain at that time. And a rule of thumb, usually any concrete mix would take about, I like to talk in terms of strain. It takes about 120 microstrain at the most. This is until the cracking. This is the cracking capacity. And usually, if your live load strain is about 1/3 of that, 30 to 40 microstrain, and your thermal is about maybe 40 to 50 microstrain, then you are left only for your mix to be controlled at 30 microstrain for shrinkage. So that's why, it's very critical to control. You can control the shrinkage usually by providing the mix design, the one that's, optimized. Also, you can control live load during pouring the concrete but you cannot control thermal unless you move it, like you said, in different times, and especially at night when the condition, the ambient temperatures are very good. So I think I would say let's assume 1/3 for each. So like this is very anecdotal, but 1/3 of each, for the total strain. So if you control shrinkage, that sometimes you control shrinkage, but then people say when we open into traffic, you have cracking, because yes, you control shrinkage, but the shrinkage is still very high. And once you add the live load, it will pop and crack. So that's I think the lesson, that this now, knowing this structural health modeling technology, the WIM motion technology, we are able to have to fuse that data and come up with a very good recommendation. So I hope in the future this methodology will be very helpful, especially in larger projects, to be able to save or minimize the cracking potential.
And we do have one question from the audience, which is, what is the next step for this WIM technology? Or also, how can this technology be applied to other states?
Checo, you want to take that on, or?
Yeah, sure. So WIM, this technology has been used, for traffic purpose, to monitor where the trucks are going, etc. And then this also has been using for bridge design. I think as the RFD design allows to use the actual traffic, in situ traffic, for when you roadway the bridge to confirm that the bridge can take the actual traffic on the road. One advancement that is moving toward these days is not only there, but also to try to reduce the overweight trucks. I mentioned earlier, for one of the example in New York City for Brooklyn Queens Expressway, now the technology is good enough to identify the overweight trucks, and then also and identify who are the owners are, and then we can send the notice of liability, so that we can try to discourage them to run the overweight trucks. And that's one way currently the states are trying to moving forward. Although the national standard is not really ready yet, but we work with the New York State and New York City in order to implement this in the WIM technology for the purpose in New York City. And then that's expanding to other states right now. And also, we are trying to do something in New Jersey. I think there are some legislation is proposed from the state senate, and then is being reviewed, and for future work.
Yeah, I would like to add, Check, with that. I think the experience, and thanks to the support from New York City DOT, who led the effort in trying to implement this enforcement or direct enforcement using WIM technology, it's been proven to be very effective. And I think other agencies in New York now are copying that model. And I think I'm aware of the state of New Jersey is also passing a similar legislation. I know there are a couple of other states that are interested, but I believe that other states can help in terms of trying to implement at least one project in their state to start thinking about utilizing this kind of technology in terms of not only for illegal overweight trucks, but also to optimize and reduce their service life cycle cost on their bridges. I mean, the less cracking, the less damage that we have on those bridges, then when you reduce the wear and tear, that's really savings in the cost over the lifetime of the structure. And I believe with NYU, we developed a couple of life cycle cost analysis for different concrete type of mixes, including those with fibers, and we implemented them on a number of projects. And there is always a benefit in trying to control the weights, the loads of the truck, but also in trying to optimize the concrete mix by adding, for example, fibers to bridge the cracks and keep them very small, which will improve the durability. So I think here the other states have really to start reaching out. There are many, not many. I mean, universities have done that, but now there are many even companies who are involved in the way in motion. The technology has improved. I know we used Kistler, but they're the quartz sensor, but now they have much better technology, digital, and there are other also vendors who produce similar accuracies. So I think, and the cost is going down, so it's not really very expensive. I think this would be something we should emulate in other states as much as we can.
Thank you.
Yeah, that was a good question, because I think the idea here is to share this technology and this approaches that we have been doing for many years. And the New Jersey Turnpike, the New Jersey DOT have been really very good supporters, and they benefited from this kind of work to make sure that they have some kind of specification that we develop for them, know what to do when they have a critical bridges and this for avoiding cracking in the beginning. I think we are getting close to time, but we still have some time for more questions. Do we have? I cannot see the chat from my side.
Yeah,
reason.
I mean, there is a Q&A box, but I don't see any open Q&A there. So
Yeah. So Mike, I have maybe just a highlight. I think it was very interesting that measuring. I mean, we tried to measure the strain from the thermal, which is really very tricky to do.
Mm-hmm.
And you measured also the strain from the shrinkage when they were pouring the concrete, right? Because you embedded these maturity sensors inside the concrete deck. And you also tried from the WIM data to get the weight of the truck. So now you really have, the model was really very well calibrated, right? Did you use any calibration for dynamic data from the dynamic deflection or from the accelerometers?
I don't believe so. I think we just went off of the estimated loads of these overweight trucks. So that's basically what we were looking. It wasn't specifically the dynamic side, but if we know that basically what their speeds are and what their weight is, we had a good idea on what that would be.
Yeah, I think you mentioned earlier that you also measured deflection or accelerometer, the displacement from the. Normally what we do is we calibrate the model for the peak strain or the shape of the strain that you are getting under the movement of the truck. But I think we did also some runs to make sure that the deflection that you are measuring is also obtained or improved by the model, right? We don't rely only on the strain profile, but we also use the deflection, because sometimes the model will really predict very well the strain values, but you would see that, oh, it's very flexible. It's not predicting the deflection right. So that model, although it gives you good estimates of the strain, but it's not the right model, right, for everything else. So, it would be good to really maybe highlight and that the modeling was done based on the strain, but also validated, using the deflection.
Yeah. So we definitely focused on the strain, but a little bit was done with the deflection just to make sure we're in the same ballpark and we're close. And even the acceleration data in this case was mostly used to just verify the strain data, but also I know Anna's study on the
Anna
dynamic.
did, yeah.
So we
it's not
tried to get
presented
as
here.
much.
Yeah.
Yeah, so
Very good.
one thing that in this case we mainly focus on the strain data, not the deflection, because of the bridge that we work on is over the river, and something we only focus on the span that is on the ground. So there is not much data we can use that, but I believe we use the strain data and then validate by the based on based on the deflection that we measure using the LDB.
Yeah, and the finite element model is mainly off of the strain data. So that was the main focus because the strain is what will cause the cracking of the bridge deck. So that was the primary focus. If the main topic was deflection, we probably would have went about it a little bit differently, but it was
Yeah.
mostly about calibrating that model for our parametric study.
Yeah, we are not, I mean, I look at the picture and people will be like, okay, I need all these people to get the work like that. This is not recommended for every bridge. This is only for critical bridges where cracking might be critical because there's a level of work involved in terms of installing the sensor and the WIM data. But this would be kind of the lessons learned from this project can be implemented on similar bridges. Right. So I think every agency now, I mean, it's getting much better. The sensors are getting much more affordable, and it might be a good idea to even embed these sensors in the new construction so that we can use them in the future. Like Jacob said, you could do the site-specific load rating based on the WIM data, but it would be also good to have some sensors like strain gauges embedded or installed in the bridge so that you can correlate from the load side and also from the bridge response side, and that would be ideal. If we could have that for bridges that are very critical and you want to get a better load rating results from that.
Yeah.
Okay, I think we're close to the time. Any other comments you wanna?
Lizzie, do you have anything that from your side that you see?
I don't, but I can add the registration link to the next Zoom in the chat, which is
Okay.
tentatively scheduled for July 30th, which is a Thursday at noon. And it is subject to change, but we're sticking with that for now.
Yeah, that one is a very, very important project. This is a very big team that from C2 Smart, we were involved in doing a lot of work for safety and the crash worthiness of bridge and roadside safety, barriers and articles. And so hopefully, we're just finishing a project for New York State DOT. I think Chico, remind me if I'm correct on this. I think it's more than 20 barriers, right? Roadside safety that we modeled, and they were also tested, which is a very big project. I mean, for the whole nation. But this will prove that now with the advances in electric vehicles and heavy SUVs and different types of loading on the trucks. Those we have a standard in the country, and this will help us look into how are these standards going to ensure the safety of the public. So this would be a very interesting project, and we'll talk about what we did in New Jersey, what we did in New York, and with other states. We've been in this line of work as C2 Smart since 2015, I would say, 2016. We've been doing a lot of work, and I think Dr. Nasruddin will be our main speaker, but there's a big involvement from Chekuk and Frank Del Conte and Dr. Osbe, and also our testing facilities will be a joint presentation, I believe, and next time. So I will encourage everybody to sign up for this one, and it's going to be really worthwhile attending this webinar. All right, I think with this, I would like to thank everyone for attending. I think this was great. Thank you, Michael and Chekuk, for your presentation. And Lizzie, thank you, and Jenny for your help in coordinating this and organizing these sessions, webinars. And I want to thank the support from New Jersey DOT for their technology transfer doing it for the Bridge Resource Program. And with this, I thank again everybody for attending and look forward to see you in the next webinar. Thank you again. Have a wonderful day.
Thank you. See you in
Thank
July.
you.
Bye-bye. Thank you. Bye-bye.